Santa Claus came by and delivered a nice little Christmas goodie for me this year. Here I have a Cambridge Decade Bridge, winner of the 1952 product name that includes the word bridge twice award. The Cambridge Instrument Company was formed in 1890 in, not surprisingly, Cambridge, England, by Sir Horace Darwin. Yes, that Darwin, son of the infamous Charles Chuck Darwin, who, as you probably know, was the founder of Chuck E. Cheese's, often considered the evolution of fine, family-friendly dining, or something like that. The company spent almost 70 years building scientific gear such as this, but actually, their claim to fame was in building the first commercial scanning electron microscope. Sadly, in 1968, they were taken over by the George Kent Group, which itself was later acquired, and presumably the once vibrant factory, a pillar in the business and academic community in Cambridge, was leveled and turned into a parking lot. This device is a realization of a Wheatstone bridge, which is a circuit that can be used to determine an unknown resistance with very high accuracy. Typically, a device like this would be used to detect shorted wires between, for example, a telephone central office and a subscriber endpoint. By measuring the resistance in a wire, you can calculate the length of the wire, and thus determine the location of a short in that wire, as the wire is going to appear electrically shorter than it should be. Sadly, however, I'm going to destroy this instrument. Well, I'm going to upcycle it. I want to do this for a couple of reasons. First off, because the galvanometer, the little meter thing here, seems to be broken. Secondly, because I have no need for this. Time domain reflectometry, or TDR, long ago supplanted the technique used in this apparatus, and I have enough junk in the lab that I can jury-rig a TDR setup if needed. What I do need in the lab, though, is an accurate Decade Resistor that I can use as part of an instrument configuration for measuring characteristic impedances of some audio projects I'm working on. A Decade Resistor lets you dial in whatever resistance value you want, and this instrument is electrically very similar to such a device. Because of that, I'm going to modify this, hopefully in a way that can be reversed, and it should make a fantastic, highly accurate Decade Resistor for the lab. There's 4 dials for resistance here. So this is 1 ohm increments. This is 10 ohms. Like I said here, 40, this would be 45 ohms. I can, this is set to 3, I can set it to 4, so 445 ohms. And then 4,445 ohms. There's also a ratio dial here. The ratio dial lets you multiply these values by a certain ratio. So it could be times 1, times 10, times 100, times 1000. When I modify this and turn it into a Decade Resistor, I'm going to have 4 decades here. I will be using the ratio switch for something, but I'll show you that later in the video. On this side we have X1 and X2. These are inputs for our unknown device or unknown resistance. And if you look at them, they're super beefy connectors, and the size of them is amazing. I mean, my pinky can fit in there. So this is designed for testing the resistance on some really big wires. It might be useful for more than just telephone wires, for example. It could be like, electrical wires as well, potentially they could have used this device for in the past. Now over here we have our galvanometer. Galvanometer is basically a standard meter movement. It unfortunately doesn't work, and you might be able to see it kind of moves around a bit, floats all over the place. I've tested this out. I've tried to make it work. I even disassembled it, but in disassembling it, I couldn't really find any way to fix the problem. So, I might try it sometime in the future to try to fix this, but to be honest with you, for now, I'm just going to leave it broken as it is. And I don't need it for what I want to do, so it'll be fine. Here we have the 2 contacts for the battery. When this is working as a Wheatstone bridge, you need a power supply, and they've actually got a little battery pack here that's been all soldered together. And Yeah, that just connects up to those two terminals there. Over here, there's two switches. This B switch connects the battery up to the circuit, and the G switch connects the galvanometer up to the circuit. Now these are kind of cool little switches because they lock, so you can twist them and they lock in place. I'm not actually going to use either of these once I mess with the internals of this, but they're cool nonetheless. One thing I really like about this is all the instructions are at the top here, and even better than that, it's in a great 1950s/1960s font. So it's just beautiful as far as I'm concerned. Here's the battery pack, and somebody at some point has taken a few cells and soldered them together, so there's 4.5 volts. I don't know what size batteries these are. I might... Oh yeah. No, it says those are D cells, believe it or not. You can kind of see it says it's a D cell. So someone soldered 3 D cells together, probably with something really hot to solder that thick copper like that. But anyways, yeah, they built a little battery pack to use with this unit. The original wires seem to be here. This used some sort of custom battery pack or some, I don't know, phone system battery pack. I don't think they're available anymore. I don't think they were available when this person built their little D-cell replacement pack. The outside of the device is a really nice, I guess this is probably oak case. Some nice brass screws on it. The handle is broken, but you know, I can probably work something out, or I could get like a local leather worker to build me a new handle if I really wanted to. And at the bottom, which is where I think you get into this thing, looks like there's a bit of a panel here, some interesting fittings. Everything's brass, all the screws are brass. It's really from a different era, so it's a cool device. A Wheatstone bridge is a highly accurate way to determine an unknown resistance. If we have our unknown resistor Rx here, and we have 2 known resistors here, and then we have a known variable resistor, we can determine the value of this resistor. And the way it works is essentially you have a current balance on these 2 leads. And if they're unbalanced, what's going to happen is some of that current is going to flow either this direction or this direction through this center wire. In the middle of the wire, you have a meter. So depending on the direction that current is flowing, it's either going to deflect this way, it's going to deflect that way, or it'll be nice and centered. The meter is going to deflect visibly even on a very small difference in resistance. The secret to this device, though, is that this resistor here, and these resistors here, which are the Decade resistors on this device, need to be extremely accurate. Otherwise, your measurement is going to be totally off here. Because this device does use very accurate resistors, it should make a very nice 4-decade resistance box once I do these modifications. I found a hand-drawn schematic for this thing online. My apologies for the low resolution, but hopefully it's good enough to describe how this thing works. At the bottom we have our 4-decade resistors. So this is your 1, this is your 10, and 100 and 1000 there. At the top we've got our ratio knob, and you can see there are a bunch of resistances. So 1, 9, 90, 400, 400. Anyways, this all sums up to exactly 1000 ohms. And depending on where you set the ratio dial, you're going to have a variable amount of resistance going through the circuit. So it'll either be 1 ohm, 10 ohms, 100 ohms, etc., depending on where this switch is. There is one setting, which is the Murray loop mode, which is right here, which will bypass all of these resistors. What I'll do is I'll use X1 and X2 as the inputs to the device. And if we sort of trace the path that that current will go through, so imagine there's a voltage here, it will travel through here, it'll travel through all the Decade resistors, it will come out here, it'll loop around, come up this wire, it will come down here, and it will go down through there, and then it's going to come to the center of this switch here, the ratio switch, and then it will travel to the battery terminal here, and it'll stop because, well, there's a switch here, there's no battery, etc. So what I'm going to do is I'm going to take the center point of this ratio switch, and I'm just going to run it right to the X1 terminal. And that will allow current to flow in a loop back out to the the device over here. And it should work as a nice little Decade resistor. Before I pull this apart, I just want to test this briefly to see how accurate it is. According to the schematic, there should be 1,000 ohms across X1 and X2 when the ratio is set to Murray loop. And you can see we've got 999.702. Now, there's a possibility that this unit is inaccurate, or my multimeter is inaccurate, or there's a temperature differential between the two. There's a number of reasons why we could be off by 0.3 of an ohm. So I'm going to test the decades and see how they affect that number. So I'm going to put that 1 ohm dial to 1, and we get 1000.702. So it is really close. I mean, it is essentially 1 ohm exactly. I'm going to switch this to 2 and 1001.706. So again, super close to what we're expecting. Bring that to 3, 1002.8. Okay, that one is a little bit off. To 3, 1003.7. Okay, again. Well, this is at 4, 1003.7. Again, it's off by that little bit. And then 5 is just way off. So it's like there's a bad contact there, it seems. And 6 works fine, but 5 does not work. So my guess is that the contacts on there are dirty, will need to be cleaned up. I bring it back to 0 ohms, and it's sitting there at 999.7 where we started. I'm going to turn the 10 ohm dial, and we've got 1009.697. So it is really close. 1019.8. Okay, that one's a little bit off. 1029.9. Again, there's a little bit of inaccuracy there, but it's very close. Try the 100 ohm dial. 1099.8. Yeah, that one's pretty good. And it should be 1199.7. See, this one is actually closer. This one is 1099.9, and it should be 1099.7. And likewise, I mean, we'll just flip this one here. Looks like it's working fine. So it seems like some of the connections need to be cleaned up here, but other than that, it's pretty darn accurate. I'm not entirely sure how to get this thing apart, but I think it might be these little brass dealies. I'm going to pull those off if I can. Looks like I can get 2 of them off by hand. I'll try this one in the corner here. And that one comes off too. Sort of the funny thing is there's actually a warranty sticker here. Guarantee void if seal is broken. And I guess the seal is this. It's got a little symbol on it of the Decade bridge. And, well, this guarantee has been void for quite some time, so I'm not concerned about it. Does it turn? Oh yeah. How do we get this open? It seems like it's turning. Yeah. It just comes off. Just turns. Perfect. Okay. Let's see if the bottom will just come off or something. Come on. You can do it. It is a mystery. So it looks like this slides out or something. So maybe I'll try to take this end piece off. Got some lovely old-fashioned brass screws, slot screws, which thankfully we don't use much anymore. I've got all the screws out, and the insides seem to have popped out. So I'm not sure how this is supposed to come apart, but I think I'm on the right track here. Look at the mess of this thing. Okay. Come on. Why is it stuck? Okay. There we go. It's still on this side. It's still connected. So it's these little feet here that you pop out, and that's how you pull it apart. So you just need to pull out the 4 brass sort of bushings or whatever they are from the corners, and then it'll pop apart. Or at least it's supposed to. This one's stuck. So everyone's fine except that last one. Oh, I just saw it move. And there we go. It is open. And what do we have inside? Ooh. Well, we've got a beautiful box. Worst case, I've got a great little box. And inside, we can see our 4 decades. And this is really cool. First impressions is it smells like oil, and not an oil I'm used to. I'm not sure what type of oil is in here, maybe a mineral oil or something, but yeah, it's definitely a little bit different. Not a bad smell, but it smells. Here's the 4 decades at the back, so 1, 10, 100, 1000. There's the switches there. They're actually interesting mechanism on those switches. They're quite complicated. All the wiring is beautifully bent in these 90-degree bends. It's all soldered. The wiring actually has, really modern looking plastic insulation. So this black plastic, these colored plastics. And that makes me think this unit is newer than I originally thought. To me, it looks like earliest this would be is, 1965. And, I don't know what the latest it would be is. But it doesn't seem as old as I thought, because on a really old piece of equipment, I would expect to see fabric insulation, different types of wires I'm not familiar with. This is, pretty familiar looking. Here's a close-up of one of the Decade switches, and you can see that each resistance on the Decade is a wire wound resistor. And these would have been very accurately made at the factory. And I would almost guess that after they wound each of these resistors, they would probably use a device like this to validate that they were the correct resistance value. The switches are awesome switches. These are fantastic. They are, if you look at these wipers here are just, basically hardcore blocks of copper. It's just fantastic. Because some of the connectors are not 100% working, I'm going to clean these up. Hopefully there's just some oxidation, and that will correct the issues that I have with some of these Decades. And then I need to do that one modification to the circuit. If we look at the circuit diagram again, my plan was to get the center tap of this ratio switch connected to X1 when the switch is in Murray loop mode. I looked the circuit over, and it's easier to do this mod than I thought it would be. All I need to do is to short this connection to this connection, and it bypasses that 1000 ohm network. And now I have a nice little Decade resistor. So I can go here and start switching things up. 113, this is the 1 ohm dial, 112, 111. That's it. So I'll just solder it up and it'll be done. I soldered those two connections together and it should be good to go. The last step is to clean each of these contacts off with iso alcohol. There's a little bit of oil on all of these, so I hope that by cleaning this, I'm not actually making things worse, but there's a bit of a green color coming off on these Q-tips, which I'm hoping is oxidized copper. So with any luck, this will make those contacts work a bit better. It's all back together, so let's test it out. Now the meter's showing about 1 or 2 milliohms. That's totally normal. I'm going to switch this to 1 ohm, and we see we have 0.9983, which is pretty good. Switch it to 2 ohms. We've got 2.004335. So, it's off by 3 milliohms. Not a big deal. 3.0004, 3.003. So it's really close. And actually, if we look at this set to 0, we'll see it's floating there around 10 milliohms or so, 1 milliohm. So having this off by 2 milliohms or so, well, right now it's even closer. That's really good. So it's quite accurate. So let's leave that at 3 and let's add 10 ohms onto it. We got 13 ohms, nice and accurate. 13 ohms and 1 milliohm. It's fantastic. We'll add 20 ohms, 23 ohms, 23.2 ohms. It's a little high, not so good. The contacts on each of these Decades, they might need a little more cleaning. I may or may not ever get to that. Gonna add 100 ohms, so we got 113 ohms. Looks great. 113.1, which is fine. And let's add 1 kilo ohm. 1,112 ohms, 0.4. Looks good. I'm going to switch these all to 0 just to take a quick look at that thousands Decade. And it's sitting at 999.47. Switch that to 2, 1999. So it's pretty darn accurate. I think this will do just fine for what I need it to. Thank you for watching this video, and I hope you found it entertaining. If you're not subscribed already, please consider clicking the subscribe button. I really appreciate all of my subscribers. Also, I'd like to thank my Patreon supporters. It's a real honor to have your support, especially in these tough times. Thanks again, thanks for watching, and see you soon.